Yeah, good morning, students. Today we'll discuss about the diffraction and polarization. Okay, in this diffraction, firstly we are having the definition of diffraction. Definition of diffraction. Okay, definition of diffraction. And then here we are having types of diffraction. Types of diffraction. We are having the two types of diffraction. That is, number one, it is Fresnel diffraction and Fraunhofer diffraction. Number one, it is Fresnel diffraction and Fraunhofer. Okay, Fraunhofer diffraction. And we are having the diffraction at a single slit. Diffraction at a single slit. Okay, and finally we are having the parameters like validity of ray optics in wave optics, validity of ray optics, or we can say with wave optics, or we can say Fresnel distance. Okay, and then finally we are having the resolving power or limit of resolution, limit of resolution, resolving power. Okay, fine. Okay, now firstly we'll come to the our first topic, that is definition of diffraction. Okay, now let us consider a source. I'm having a source of light. Okay, whatever be the shape, either it may be spherical or cylindrical or plane. Okay, whenever it passes through a slit, then what will happens, initially we'll have the source will emit the light waves. Okay, whenever it obstructs or whenever it will strikes the any optical instrument, either it may be slate or it may be prism, it may be lens or it may be mirror, okay, or it may be microscope or it may be telescope, any optical instrument, then the path of the light rays will be deviated or will be changes. Okay, suppose initially here it is, then the light ray, okay, here the wave will be in the form of a wave. The light will be in the form of a wave. So light ray will changes its path. This phenomena can be called as diffraction. Okay, the phenomena of traversing the light ray when the light ray is incident on any optical instrument is called as diffraction. Okay, the phenomena of traversing the light ray when a light ray is incident on any optical instrument can be called as an diffraction, can be called as diffraction. Okay, okay, fine. And here also the same thing, the light ray will changes its path. Okay, and whatever the light rays are changes its path. In order to see, here we are having a screen, here we are having a screen, and this one it is slit. Okay, okay, fine. Now there is a distance between the slit and the screen that we are calling it as capital D. Okay, which we have learnt it from the interference in the Young's double slit experiment also. We did the same thing. Okay, that is the distance between slit and screen, it is capital D. And let us consider small d is the, this distance is the distance between the slit. Small d is the distance between the slit. Okay, this slit distance will be very much, okay, comparable with the wavelength of the light. with the wavelength of light. That is my definition. And coming to the types of diffraction, based upon the slit and screen, if slit and screen are at finite distances, if slit and screen are placed at finite distances, then we can call it as an Fresnel diffraction. If the slit and screen are placed at infinite distances, okay, infinite distance means that, okay, in real time application, we can say that slit and screen are placed at far distance, at far distance, okay, then we can call it as an Fraunhofer diffraction. Then we can call it an Fraunhofer diffraction. Okay. Okay. And then next one, it is diffraction at a single slit. Diffraction at a single slit. That means here I'm having a source such that I'm having a single slit. Okay. Here the light rays will incident. Okay. Here the light rays will incident in the form of a wave. In the form of a wave. And here we are having a screen. We are having a screen. This is the screen. Okay. Okay, fine. Now some of the light rays will passes through the at the middle point of the slit. That ray will not get deviated. Okay, that ray will not get deviated. So before incident of the slit, this ray, whatever the energy it will have, the same energy it will also have. So this can be called as undeviated ray. Undeviated ray. Okay, which we can also call central fringe. After diffraction, what will happens? After diffraction, what will happens? The light ray will get deviated. Okay, suppose like this. Similarly, from the other end, like this. Okay, okay, fine. The light ray will get diffracted. Okay, soon after the diffraction of the light rays, okay, these two light rays will superpose on the screen, which will use a fringe P, and this will use the fringe Q. Okay, the distance between the central fringe and this one, okay, I am calling it as yn. And similarly in the bottom, similarly in the bottom. Okay, okay, fine. Now here it is that, here it is that you can see, if I draw a perpendicular, I am calling it as m, this distance as d by 2. And similarly, I'll draw a perpendicular here. This distance as d by 2. D by 2. Okay, I'll call it an n. I'll call it an n. Now, whenever the light ray is diffracted, okay, some of the light rays will reflect it back. Some of the light rays will reflect it back. So, this is my reflected ray. This is my reflector ray. Okay, and here it is. This is my reflector ray. Now, likewise in interference, here also I want to find what are the conditions to get the maximum intensity and minimum intensity. Here, the light rays are undergoing the process of diffraction. Okay, so firstly, I need to find path difference. I need to find the path difference. Let us consider this one as S1 and this one as S2. Okay, So path difference, I can write it as, okay, path difference, which is indicated by delta, that is S2P minus S1P. In order to find the path difference, here what I am doing it is, I am drawing a perpendicular such that you can see this one. This is the angle theta. Okay, this is my slit width. Okay, which I consider it as D. So the path difference, it is nothing but, suppose let us consider this as X and this one as Y. It is nothing but, okay, this as Y. Okay, path difference is nothing but XY. So XY I need to find from the triangle S1XY. Okay, S1XY. Okay, I can say that S1X S1X will be equal to D. So XY is equal to D sin theta, is equal to D sin theta, this one. Okay, so path difference will be D sin theta due to refracted or diffracted rays. Okay, and there will also be path difference between reflected rays, these reflected rays and diffracted rays. So you can see the angle between, the maximum angle between reflected rays and diffracted rays will be maximum, it will be 180 degrees, or we can write it as pi radian. Whenever we are having the phase difference as pi, I want to find the path difference. Since we know the relation between the phase difference and path difference as phi is equal to 2 pi by lambda times delta. So pi is equal to 2 pi by lambda times delta. So delta is equal to lambda by 2. So total path difference it is d sin theta plus lambda by 2. Right? Okay, called as equation 1. In order to obtain the bright image, okay, or constructive pattern, constructive diffraction, okay, to obtain bright image or constructive diffraction, bright image or bright fringe. Okay, we can write as d sin theta plus lambda by 2 is equal to n lambda. So d sin theta is equal to n minus half times lambda. That is the condition for to obtain the maximum intensity or bright fringe in the diffraction. Similarly, to obtain dark fringe, dark fringe, okay, the total path difference must be equal to 2n plus 1 times lambda by 2. So that is d sin theta equal to n lambda. D sin theta is equal to n lambda. That is the condition to obtain the dark fringe or destructive pattern. Destructive pattern. Okay, that is. So that means here we can say that this is the theta, and we can say from this triangle here it is theta. Okay, so we can say that with respect to the center, we can say the angle. So theta I can write it as, or tan theta I can write it as yn by capital D, opposite side by adjacent side. With respect to center, if I consider theta, this triangle, okay, this is the yn and here it is D. So when theta is small, when theta is small, I can write as tan theta is approximately equal to theta. So theta equal to yn by capital D. Yn by capital D. Okay, that is what the diffraction at a single slit. Okay, and let us consider A is the, okay, slit aperture. Okay, A is the slit aperture, and now we are having that it is now we are having lambda is the wavelength of the light ray, and A is the, okay, A is the slit width. Now the Fresnel distance is given as the Fresnel distance, okay, ZF is given as a square by lambda. Okay, in order to have the validity of ray optics in wave optics, okay, this the slit width must be very small than the wavelength. So it must be very less than 1. A square will be very less than lambda. That is the condition. Okay, that is the condition. Okay, okay, fine. And then finally, resolving power or limit of resolution. Resolving power is defined as, okay, before going to see the resolving power, I will tell the limit of resolution. Limit of resolution. Limit of resolution means it is the smallest distance or smallest linear or angular separation between point objects which they can clearly seen or clearly seen by the observer, okay, or by an optical instrument can be called as limit of resolution. Okay, see, sometimes what will happens on the railway platform, suppose if two persons are standing, A and B, okay, suppose one of the person can say that train is coming and he can able to see it, okay, from the far distance. That means that student is having the, or that person is having the more resolving, okay, from far distance also he can see very clearly, can see very clearly. It can be called as limit of resolution. Okay, the smallest linear or angular separation between two point objects, between two point objects at which they can see okay, clearly or resolved by an optical instrument, can be called as limit of resolution. Limit of resolution. Now, resolving power, it is the reciprocal of limit of resolution. Resolving power can be defined as reciprocal of limit of resolution. Limit of reciprocal of limit of resolution can be called as resolving power of telescope. Okay, here we are having the resolving power of microscope. It is 1 by d. This is for microscope. Resolving power of microscope. We are having the direct formula, that is resolving power equal to 2 mu sine theta, where mu is the refractive index, theta is the angle of diffraction, by 1.22 lambda. Resolving power equal to, okay, as the medium changes, the refractive index will be changes. Correspondingly, resolving power will also be changes. Okay. Whereas for telescope, it is resolving power of telescope. Resolving power of telescope, that is capital D by 1.22 lambda. Capital D by 1.22 lambda. Okay, 1.22 lambda. That is the resolving power of microscope and telescope. Thereafter, we are having up to here it is diffraction. Up to here it is diffraction. Okay, all of you please note down. Okay. This is the diffraction at a single slit. Keep the side heading. Diffraction at a single slit. Okay. Next we are having the polarization. Okay. Next we are having polarization. Okay. Okay, fine. Now, even you can see this polarization, you might study the definition in electrostatics. In electrostatics, we are having the methods of charging. Methods of charging. In that, we are having one of the method, it is polarizing. Okay. By polarizing a substance, we can charge it. We can charge it. Okay. Okay, fine. That is, suppose I'm having a source of light. I'm having a source of light. This source will emit the light rays in the form of the waves in all the directions, like this. In all the directions. Okay. Whenever I place an optical instrument, okay, suppose let us consider I'm having a mirror or slit, such that only these three light rays will participate in the incident of the optical instrument. The other light rays, okay, will goes in the other direction of the optical instrument. So we can consider that these light rays are moving in the other direction. So it will be an waste. Okay. So here we, due to these light rays which are moving in other directions, okay, we are losing the light energy. So now we want all the light rays to travel in one direction. Okay. Even in the magnetism also, what we consider it is, I'm having a material. If I apply a magnetic field, then all the dipoles will be aligned along the direction of the field. Will be aligned along the direction of field. We are calling it as an magnetization. Aligning all the dipoles along the direction of the field can be called as magnet. That is, aligning all the magnets means we'll get the magnetic moment per unit volume. Per unit volume, we can call it an magnetization. Okay, the same thing here. Suppose after passing the mirror, after passing the mirror, all the light rays, you can see this one. And light rays are the examples for the transverse waves. So always it will have the vibration perpendicular to the wave propagation only. Okay, suppose this is my direction of propagation, then we are having that it is vibration of particles will be perpendicular. Okay, like this direction only will have. Okay, that is the arrangement or alignment of particles to move in unique direction can be called as polarization. Okay, for this we are having the two devices. Suppose I'm having an source that is which can travel in all the directions. If a light ray can travel in all the directions, we can call it as unpolarized light. Unpolarized light. That means it will travel in all directions. Okay. And now polarized light. Polarized light. It means that it will travel only in one direction. It will travel only in one direction. Okay. Now, in order to obtain the polarized light, here we are having a device called polarizer. Polarizer. Whenever the light is incident on the polarizer, okay, here I am having an I naught is the intensity of the unpolarized light. All these are unpolarized light. Okay. After polarizer, okay, we will get a light. I don't call it as an polarized light. Okay, because whatever the light obtained, we must check it, right? We must check it and thereafter we should confirm it. We cannot say that it is polarized light. In order to check it, we are having a device called analyzer. Okay, this polarizer and analyzer, usually it is made up of with an ferromagnetic crystal like nickel or chromium, okay, or steel, okay, like this ferromagnetic crystal will be. Whatever the light is obtained from the analyzer, it will be polarized light. It will be polarized light. Okay, not always every time we'll have the polarized light will be perpendicular like this. Sometime we may have, okay, we may have like this, like this. Okay, that is with respect to axis, it makes an angle theta. This is the I naught. Okay, so with respect to this, what Malus explained that the intensity of polarized light, okay, is directly proportional to cos square theta. Okay, theta is the angle made by the polarized light with respect to the undeviated ray or with respect to the axis. With respect to axis, and I naught is the initial. Okay, so intensity of the polarized light, we can say that it is I naught cos square theta. Okay, see here intensity it is becomes into half. Intensity becomes into half. That's why we'll write it as I naught by 2. Okay, intensity of unpolarized light it is, we can write as I naught cos square theta. Whereas for polarized light means we can write as I naught by 2 cos square theta. Students, please go through the numericals on this Malus law. Most important. Okay. From last 3 to 4 years, every time they are asking, one question on this Malus law. Okay. Say for example, let us consider I am having the three polarizers P1, P2 and P3. Three polarizers. When a source of light is incident on the first polarizer, such that, okay, we'll get a polarized light which will falls on P2 and P3. Suppose I'm having a source of light. Initially, these polarizers, one is, first polarizer is kept along x-axis. This is P1, okay? And the third polarizer is kept along y-axis. This is P3. P2 is kept at an angle. P2 is kept at an angle 60 degrees. P2 is kept at an angle 60 degrees with respect to P3. So with respect to P3, 60 degrees means, or with respect to vertical 60 degrees means, with respect to horizontal, can I say 30? 30 degrees. Okay. Okay, fine. Now I am having a source, okay, which is emitting the light rays in all the directions, falls on the polarizer P1. So whenever the incident light is incident on the polarizer P1, it is an unpolarized light having an intensity I naught. Whatever the light rays are emitted, okay, here it is. After the first polarizer, we can say it is a polarized light. So I1 is equal to I naught cos square theta. So it is, in order to have the maximum value of intensity from the first one, okay, we are considering that theta is 0. When theta is 0, intensity will be maximum. So I1 is equal to I naught by 2. This one it is I naught by 2. Okay, unpolarized light it is I naught by 2. Okay, polarized light I equal to I naught cos square theta. Now, this polarized light is passed onto the second polarizer, which makes an angle 30 degrees with respect to P1. So I can write as I2 is equal to I1 cos square 30. I1 cos square 30. That is I1, we got it as I naught by 2. So we can write it as I naught by 2 times root 3 by 2 whole square. That is 3 I naught by 8. Intensity of emitted light from the second polarizer. Now, after the second polarizer, if you see, the light ray will emit on the, or incident on the third polarizer. On the third polarizer. Okay. Soon after this, light ray will get emit like this. So intensity from the third polarizer. Okay. I2 cos square. Angle between P2 and P3, it is 60 degrees. See. So I can write it as cos square 60. That is I2 means 3 I naught by 8 times 1 by 2 whole square. So I can write it as 3 I naught by 32. So in the question, they may ask the what is the intensity of the emitted light from the second polarizer, or what is the intensity of the emitted light from the third polarizer. This model is the most important with respect to your board and with respect to your entrance. With respect to your entrance. Okay. So Malus law explains that for unpolarized light, I is equal to I naught by 2 cos square theta, or polarized light means I naught cos square theta. Okay. Please remember this one. And in the question, carefully see whether it is a polarized light or unpolarized light, because this divided by 2 will cause the difference. This causes the difference. Okay. And next, finally, it is we are having the Brewster's law. Brewster's law. Suppose let us consider an medium. Okay, I'm having an optical substance. This is rarer medium having an air as the medium, and this is that my denser medium. Denser medium having a refractive index as mu. Having a refractive index as mu. Okay. Now let us consider an incident wavefront. Incident wavefront. Okay. Incident wavefront which makes an angle I. Okay, which makes an angle I. Let us consider AB is my wavefront. Whenever a light ray is incident on an optical substance, then what will happen? Since it is a wavefront, okay, so Brewster explained that some part of the light ray will get reflected, will have reflected wavefront and refracted wavefront. Since it is light ray is moving from rarer to denser, so the refracted ray will move towards the normal. Will move towards the normal. Now, according to the properties of wavefront, Brewster considered that angle of sum of the angle of incidence and angle of refraction will be 90 degrees. The incident wavefront will be perpendicular to the this refracted wavefront. So by applying the Snell's law, by applying Snell's law, by applying Snell's law, we can write it as air air medium or mu r into sin I is equal to mu d times sin r. Since rarer medium I consider as air, so 1 into sin I is equal to denser medium is having a refractive index mu. Since I know that I plus r equal to 90, instead of r I can write as sine of 90 minus I. So that is sin I is equal to mu times cos I. So mu is equal to tan I, where I can be called as angle of incident wavefront or angle of polarization. Okay, the angle at which the light ray is incident, such that here we'll get the light as polarized like this. Light as polarized. Okay, here in the incident wavefront, light ray will be unpolarized, angle of polarization. Okay, in the MSET or BITSAT or in any state entrance exams, private engineering entrance exams, will have this Brewster's law. We are having this Brewster's law. Okay, fine. That is what your polarization. Okay, diffraction and polarization. Okay.